these sigma and pi bonds, we gave a key to say the easier way to identify these bonds is by just looking at the order to say whenever it's a single bond. So we said whenever it's a single bond, just know that you're dealing with a sigma bond. Then whenever there's a double bond, just know there's a sigma, then there's a pi bond. Whenever it's a triple bond, just know that there is a sigma and there are 2 pi bonds. So that's basically what you have. Yeah, that's what we said. And aside this, we also mentioned to say the type of hybridization that you find in each bond is going to be varying, and we defined hybridization to just be the mixture of orbitals. That's what we simply discussed, right? Yeah, so that's what we said. And in a single bond, we say there's always going to be an sp3 type of hybridization, and in a double bond, we say there's always going to be an sp2. Then in a triple bond, we say there's always going to be an sp type of hybridization. So now this is what we were doing last time. This is where we ended from last time. So now I want us to continue by looking at the application of the VSEPR theory. Yeah, so just a minute. Yeah, the VSEPR theory, which helps us to identify the type of structures that we'll be dealing with. So whenever we're trying to write a molecular structure, the first thing that we need to identify is the number of electrons in the valence shells. Yeah, so we did discuss, I explained how the hybridization thing forms. I explained how sp3, I did explain everything else. So here today, I just want to start on something that will be better use. So I'll start with these guys here, Lewis structures. Okay, I think this will help. Okay, so if I was to give you something that looks like this, so I'll start with a normal example. I'll just start with an example. The test 1 for the other year is loading for 2021. You'll see how the questions are going to be phrased. Yeah. So if I ask us to write the Lewis structure, to say, write the Lewis dot structures of, let's say, molecules, I write there is ammonia. I'll say ammonia. Let's say 2, we have, let's say we have hydrogen sulfide. Let me use something like this. Then you have something you are familiar with. I'll use this guy. Then from here, I'll also say, so right, the question is, the Lewis dot structure. Yeah, that's what you have. So we said the first thing we need to do, this is the last thing that we discussed last time. We said the first thing you have to do is to write the valence electrons for everything. So here we're simply going to say nitrogen has 5 in the outermost shell. So we're having this. So we have the total valence electrons. So we're saying total valence electrons. We write something like this. So nitrogen has 5 in the outermost shell. Each hydrogen, there are 3 of them, each is having 1 electron in the outermost shell, giving us a total of what? A total of 8. And we have a total of 8 electrons that we need to distribute amongst, or rather within nitrogen and the 3 hydrogen atoms. That's what we want to do. So we're simply going to have nitrogen as the central atom. The reason is that nitrogen needs 3 more for it to be happy, because it has already crossed the number here, which is half of 8, right? So this number 5 only needs 3 more electrons for it to obey the octet rule, for it to have 8 electrons, or for it to be stable. That's what we are saying. So now we are going to have nitrogen on the middle. Then I'm going to put the 3 hydrogens near nitrogen like this. So we put the 3 hydrogens, and we have to distribute the 8 electrons. Now, keep in mind that each hydrogen only needs 1 electron for them to be happy. So I'll put 2 electrons here on the middle, and I'll also put 2 electrons this side, and I'll also put 2 electrons here, meaning this hydrogen is happy, this hydrogen is happy, this hydrogen is happy. Then you have your nitrogen, which is like this. So the attached atoms, which are also called the actual atoms, these are actual atoms. So once these guys are happy, now we can think about satisfying the central atom. Or rather, we can just say we throw all the remaining unutilized electrons on the central atom. So we had 8 electrons, we've only used 6. So we have 2 lone electrons that were not utilized. And we can simply write this nicely by saying whenever there are 2 shared electrons, we can always represent them with a single line. So we have hydrogen with a single line to this nitrogen, and we have another single line this side to this hydrogen, and another single line to this hydrogen. Then there are 2 lone pairs, so we indicate them here on top. This is basically what you get. So this right here is the Lewis structure of nitrogen, with ammonia, NH3. This is what we get. Is there anyone, guys, who is lost up to this point? This is where we ended from last time. I was just explaining how we get the Lewis structure. Is this okay? Is everyone okay with this? Anyone, any questions, guys, here? So in the paper that I'm from sending, there is question 8A that I'm going to do. I needed a question that is coming from an odd test paper, so at least we have a proper question now. So when you open the document, you'll be able to see it, but I'm still sending a screenshot regardless. We want to write the Lewis structure of POCl3. That's what you have. So if you're okay with this, I'll leave it at that. We're just writing the Lewis structure, that's all. Then I want to write this guy here. This is in the test paper that I'm from sending. So now, how many valence electrons, or rather how many electrons are in the outermost shell of phosphorus? Anyone sitting with a periodic table, guys, what's the valence the valence number for phosphorus? How many electrons are in the outermost shell? John, how many electrons are in the outermost shell for phosphorus, for P? The 32 electrons, because here we got the total number of electrons to be 32, and we say the first thing that we need to do is make the outermost shell atoms, or rather the surrounding atoms, to be happy. We are not worried about the central atom. In this case, phosphorus is our central atom. It can either have more than 8 electrons or less. Provided the attached atoms are happy, the whole molecule is going to be said to be stable. So this is simply what you get, and this will be the Lewis dot structure of the molecule that we were given. Now, how do you know this is the correct structure, right? How do you get to confirm? What if someone else thought about this? What if someone says, okay, so phosphorus could have formed a double bond with oxygen, then a single bond with this guy, but then again, look at this, the confusion now, because they are chlorine, each chlorine can only form one covalent bond. So we cannot force a chlorine here, because phosphorus can only manage to form a number of 3 covalent bonds, because it has a valence number of 5, meaning it just needs 3 more. So this could not have been possible. The same thing even in water. I'm just explaining this so that you understand. Why do we write water like this? Why don't we ever write water to be like this? Why not this? Why do we always go with this? Because we cannot have a hydrogen atom forming two covalent bonds. Each hydrogen can only form one covalent bond at a time. So that's the reason why this cannot be possible. Now, how do you confirm that the structure you've drawn is correct? There is what we call the formal charge. So you have to calculate the formal charge of the whole molecule for you to be assured that what you've done is a correct thing. So there is this formal charge calculation that you need. So formal charge calculation, the formula is Fc is equal to the valence electrons before it's bonded to anything minus the number of bonding electrons, or rather bonds, let me just say bonds. So some people say, I'll give you the two versions of the formula. Some people say bonds that it's forming, then minus the lone electrons. Yeah, the lone electrons. Or some people say the answer is still the same. Formal charge is the valence electrons. So valence electrons minus half the bonding electrons, then minus the lone electrons. So either way, you should get the same answer. So when I say number of bonds, so here, for example, I want to calculate the formal charge of P, which is phosphorus. So formal charge of P is equal to how many valence electrons does P have before it's bonding to anything? It was 5, right? Then minus how many bonds are you seeing? How many lines are connected to P? There are 3 of them. Then minus how many lone electrons? Are there any electrons on P that are not bonding to anything? So there are no lone electrons. So the answer there is what? It's a 2. Then again, we can do the same for this chlorine. We're saying for this chlorine, the formal charge would be the valence electrons were 7 minus how many lines or bonds are you seeing? There's only 1. How many lone electrons are you seeing? There are 2, 4, 6. There are 6. So the answer here is going to be what? 0. That's simply what? That's your formal charge for this. Now you notice that they all have 0 because they are all looking the same. So even this guy, the formal charge will be 0. Even this, the formal charge will be 0. How about for oxygen? So formal charge of oxygen will be 6 minus the number of bonds is 2. The lone pairs is also what? The lone pairs is there are 4 of them. So you notice that the total thing gives you what? 0. So this is also a 0. So when you add everything, it's simply going to give you, because 2 plus all zeros, meaning the overall formal charge is just a positive one. It's a positive 2. Meaning that this guy lacks 2 electrons for it to be happy, which is true because it only has 6. 2, 4, 6. It's insufficient. It's not obeying the octet rule, but it's fine because it's a middle atom. But we're just saying if we were to make it stable, we need 2 extra what? Electrons. Any questions, guys, here? Maybe I'm too fast. Is there anyone who has any question? So I'm not on the Google Meet thing. You can just unmute yourself and I'll be able to hear you speak. On how to put these dots here, the ones for electrons, these ones here. Okay, so when you look at your whole molecule, so you need to decide by the number, the atom that has a bigger valence number, the one that needs more electrons, that's the one that you use to decide. So in this case, you look at the numbers, because here on getting the total valence electrons, it will show you. Phosphorus has what? Has 5, meaning it needs 3 electrons. The one that can form the more bonds, it's the one that's going to be on the middle. So phosphorus can form more bonds because it can form up to 3 because it needs 3 extra what? Electrons. Oxygen can only form 2. Then followed by chlorine, which can only form what? 1 because it has 7 electrons. Just needs 1 more electron. Yeah, so the P is the one that we put here on the middle. So when arranging, you put the P close to the oxygen, knowing fully well that the P is the one that's the parent, it's the parent atom in this case. And then we said, since we know that the chlorine atoms can only form one covalent bond at a time, they just need one extra electron. So we're distributing 2 to chlorine, then we're also distributing 2 to this chlorine and also 2 here. Then oxygen just needs 2 electrons. So it's already bonding with chlorine, meaning it will just have to bond again with the phosphorus here. And we had 32 electrons. So now we want to distribute all the 32 electrons to satisfy the outermost atoms. And the outermost atoms are the ones that are this side. These guys, these are the outermost atoms. These guys. So we need to make sure that they are happy. And they can only be happy if they have 8 electrons. Each one here is only having 2, with an exception of oxygen, of course, because we have given oxygen 4 because of this. So oxygen just needs 2 more. So it has become happy. So oxygen is happy. You are seeing it there. It has the 2 electrons. Chlorine is not yet happy. This chlorine needs 6 more electrons. So we give it the 6 electrons. This guy as well here, it has the 2 but not yet happy. We need to give it the other electrons. So, okay, just a minute. Okay, so we need to give it 6 electrons as well. So this is basically what we're doing. I suppose that was Harry or Mapalo that was asking. So you'll get something like this. So now we count the electrons. You'll notice that the electrons will never finish until the outermost atoms are satisfied. So you have something like this. This is basically what you're having. Now we count the electrons. Have we used all the 32? We have 8 here. We have 8 here. We have 8 there. That's a 24. 24 plus your 24, 26, 28, and 32. So we've used all the 32 electrons, meaning we have no electrons left to give P. So it's okay because it's a parent. It can either be happy or not happy. We're only concerned about these guys here outside. Yeah, so this is how we come up with this structure here. If there were 4 electrons, a perfect example I can give you is maybe this will make more sense. Carbon dioxide. So carbon has 4 in the outermost shell. There are 2 oxygens. Each oxygen has 6. This is going to give you 4 plus 12. This will give you 16 electrons. So we need to share 16 electrons between 1 carbon and 2 oxygen atoms. Now, carbon needs 4 more for it to be happy, and oxygen just needs 2. So we'll put carbon on the middle. This is your carbon. Then you put an oxygen atom this side and an oxygen atom this side. Then we know to say each oxygen needs 2. So it already has 6. Maybe I may write the 6. So it already has the 6. Each oxygen already has 6. Like this. So I'm putting the atoms, the electrons for oxygen in red. Then each carbon is only having 4. So it will share 2 with this oxygen and 2 with this oxygen. So this is going to create a double bond because here you had 4 electrons. Then the 2 lone pairs will be there. Carbon with a double bond with another oxygen. This here will be your Lewis structure for carbon dioxide. Is this okay? Any questions, guys, here? Sulfur is alone. These guys here, there are 3 of them. So we'll put the single atom to be the middle one. Then we'll put the other 3 guys to be this side. So each of them can either have, so here I'm going to put this. So I want you to pay attention to what you're going to see here. Then this one is already happy, just needs 2 more. And then this one here needs to be happy, so we'll put it like that. Then we're having what? This is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, something like that. Then we'll put the extras will simply be, this is what? This is 8, this is 8, this is 8. So we're having 2 more extras. So we'll put the 2, push them here on the middle. So this can be recreated and be rewritten as to just reduce this so that you see the whole thing. You have a sulfur relating to an oxygen with a single bond. Then you have a double bond here with 2 this side. Then you have a single bond this side. You have something like that. Then you have the 2 extra electrons will be there. Then you indicate to say this one has an extra 2 electrons, so it will carry a partial negative charge. So here we need to indicate that this guy has a negative 2 charge. So this is a negative 2. So you can leave it at this. Now, if you are using Zoomda, this guy here, they'll tell you to say this is going to show you resonance behavior. By resonance, we mean that the double bond that you see here can continuously be rotating to be around any of these atoms. So maybe if I was to show you to say, let's imagine this is atom number, oxygen number 1, this is oxygen number 2, then this is oxygen number 3. We know they're all oxygens, but all we're saying is, in resonance, what we mean is that the double bond could have been shifting because it could have been anywhere. So to avoid the biasness, we would have just written it like this. The double bond there, you have your what? You have your S, this oxygen, or you could have had the S, the double bond is there, you have this oxygen there, you have this oxygen there, or the double bond would have been there, the double bond would have been on the other side, you have this. So these 3 structures would have been possible. And this is what we call resonance. Resonance means that you have a structure that can take up many forms at once. So you cannot catch one molecule at a time because the double bond is continuously flipping between the oxygen atoms. That's what we mean by resonance. Yeah, to say the double bond here could have been anywhere, and it could have been either on oxygen number 1 or 2 or 3. So it's continuously going to be spinning and it's going to be moving in that direction. Yeah, so it went in that direction. So this is what we call a resonance type of structure. Any questions, guys, here? Formal charge. The smaller the value of the formal charge, the stable the molecule is. That's basically what you need to know. Yeah, so this explains why it's easy for you to only have one Lewis structure, because if we get different Lewis structures, you'll notice that the formal charges will also be different. Yeah, so let me give you, okay, so the answer to those guys here are actually given, so let me send them right away. So if there are no questions here, then I can proceed to the part that I wanted to focus on, which is on this part where we have to give the geometry of the structure that you are dealing with. So whenever you look at a molecule, by now you should be able to identify what type of shape, what type of molecule you're dealing with. By shape, we mean what's the name. For example, water, right? You learned from biology to say water is a bent structure, or rather it's V-shaped. The reason why that is so is because, where is that guy here? So water falls in which category? You're having water is like this, H. Okay, so let me just say you have H, O, you have H, then you have 2 lone pairs there on top, right? So if you go here, you have to master this table. You have to sort. I sent this as the handout last time after the previous class we had. So you look at the number of electrons. How many things are bonding to the central atom, right? That's the thing that you ask yourself. Now, if you have something like water like this, so when we say things that are bonding to the molecule, we mean even these electrons are going to be counted. These are going to be called lobes of electrons. So they will be like this. So on counting, you count them together. So there will be 4 things. 1, 2, 3, 4. Those are 4 things that are hanging to what? Towards water, on the molecule water. So that's what we mean by a group of electrons. There are 4. That's the pairs that you see around what? Around the oxygen. Now, if you have 4 of them, what else? What other criteria do we have? The bond angle is here, and we're saying the best geometry is that it should be a tetrahedral. But how many lone pairs are you seeing on the central atom? If there are 2 lone pairs, the actual shape name will be what? Will be bent. That's how we come up with the name to say water is a bent structure because it has a what? Because it has 2 lone pairs on the what? On the oxygen, or rather on the central atom. So now if I give you this, the previous guy we are from discussing, let me show you this. How about if I ask you this, NH3? This was something like this. There was a lone pair there. Then there is H and there is H. So what's the name of this? You go on the same table. Okay, there are 4 things attaching to nitrogen. We also count the lone pair. This thing here is a lobe of electrons. It's representing the 2 lone pairs. Those, yeah, they're in a lobe like that. So we are counting 4 things that are connected to nitrogen. So that's 4. So we are in number 4. So how many lone pairs do you see? How many lobes do you see here? It's just what? It's just 1, right? So here, this name, the name of ammonia, or the shape of ammonia is simply trigonal pyramidal. And the hybridization is sp3 because we said whenever you see single bonds, all the bonds here you see are all single. So meaning that's simply sp3 hybridization. So you have to master this table of these shapes. I hope you guys are following here. Any questions, guys? Any questions here? Okay, so if there are no questions here, there is something explicit that they give you here. It explains the same thing as well, but more detailed. We're just focusing on the ones that they'll be asking you most of the times. So they'll be asking you about a tetrahedral, a trigonoplanar, a trigonopyramidal. You have to know how these guys look like, much more to tell us the type of hybridization that's present. So what we mean by hybridization is the mixing of orbitals. So if you have a combination of more than one orbital in a molecule, or one hybridization, for example, if I give you something like this and I ask you to say what's a hybridization in this, imagine there was something like this. So here you are having a double bond and single bonds throughout. We said sp is more important than sp2, then sp2 is more important than sp3. Not really that it's more important, but we're just saying it's more respected. The order of priority is that sp, which is just always going to be found in a triple bond, is more respected than the one found in a double bond, then followed by the one in a what? In a single bond. So if they ask us what's the hybridization of this molecule, the one that we're able to see that we give more respect is sp2. So we're saying this overall molecule has sp2 hybridization whenever there's a double bond present in the what? In the molecule. Is this okay, guys? Yes, it's sp2. Yeah, so it's sp2 here. How, if I was to give you something that looks like this and give you something like this, give you that, to say what's the hybridization in this molecule, you say it's sp because this triple bond is important than the other type of the double bond and the single bond. So here the dominant one is what? sp hybridization. Yeah, so whenever you have, we're just saying this is more important than that, and then this is more important than this, and then obviously meaning the triple bond will be important than the what? Than the single bond. So this is basically what we are saying. The one that has more bonds or more pi bonds is the one that we give more respect. Yeah, that's what we have. Okay, so if this is okay on this part, on this note, this is okay. Did give you the way that we write the configuration. It's called the SPD notations, SPDF notation. You'll see the question on question B4D in the paper that are forwarded. They're simply saying, draw the ground state electronic configuration using the SPD notation for the following species. So there is copper and chromium. So I did emphasize to say whenever you're writing the configuration, expect this question to come in your test, or rather in your quiz if anything. Whenever you're writing the configuration for copper has what atomic number? Is it the one that has 24? What's the atomic number for copper? Is it 24 or 29? Okay, so if it's the one that has 29, I always switch these with chromium. So if it's the one that has 29, meaning chromium has 24. Now, according to our question, the question has specifically asked us to write the configuration of chromium 3+. Yeah, so meaning they removed 3 electrons from the 24, so we're dealing with 21 electrons. So copper is still intact. Whenever they ask for the configuration of copper or chromium, you give them 2 types. So for copper, you give them to say the expected one, according to the formula, the expected one is 1s2, then 2s2, then 2p6, then you have what? 3s2. So we just follow the formula. Then you have 3p6, you have 4s2, then you have 3d what? 3d, this is what? This is 10, 10. That's going to be a 9, right? This is what you have. This is what we expect if we were to follow the formula. But the actual one, you have to give them both answers. No wonder you see that the person there was just given half mark. Yeah, because they didn't even write actual expected. They just wrote things. They were just given, I think, for the effort because they followed the formula, but the answer was wrong. The actual one, we simply have 1 electron from the 4s will be given to the 3d. So this is going to be 2p6, 3s2, then 3p6, then 4s1, then 3d, 10. So you always give them actual and expected. Write it the same way I've written it here. Or if you don't want, you can write it using the shorthand notation using argon. I taught you how to write this. So argon has 18. So we have this. This is 18. So we can shorten it. Then you just write this. This is just 4s2. Then you have 3d, 9. This will be the expected one. Then the actual one would have been argon. Then 4s1, then you write 3d, 10. That's your expected and your actual. So because argon is a noble gas, which is a subset of, which has a configuration, which is a subset of the configuration of copper, no wonder we're using it here. Yeah, it's the closest noble gas. Yeah, then for this chromium here, chromium was supposed to have 24, but there's a positive 3 on top, meaning it has lost 3 electrons. So this is going to be 1s2, then you have 2s2, then you have 2p6, you have 3s2, you have 3p6, then you needed to have 4s2, then you need to have 3d. Initially it was supposed to be 24, right? So this is supposed to be, I think it's supposed to be a 3 or something, is it? Or a 4? Yeah, it was supposed to be a 4. Then we always say that if this is the expected one, right? If there were 24 electrons, but then here they've already subtracted 3 electrons from this guy. So now let me just rewrite this because it would be wrong if I say that this is initially this is chromium if it had 24, and then we always say that we give 3d more respect than 4s. So the actual one should have been 2s, 2s2, then 2p6, then 3s2, then 3p6, then 4s1, then 3d5, because we are saying there is no way that 4s can be happy when 3d has failed to even reach half. Because of this, we change it to this. You are seeing we're getting 1 electron from the 4s and putting in the 3d. Now, according to how the answer was supposed to be, because we need to now get the electron from, we need to get 3 electrons away from this chromium thing. So we needed to get an electron from the 3d. So this, let me just give it to you here. So it was supposed to be, okay, let me write the way they wrote it for you. So we need to write, or rather remove electrons. Here is going to be 1s2, this will be 2s. This for chromium 3+, this will now be, we have 2p6, it will be 3s2, it will be 3p6, it will be 4s0, then it will be 3. We have removed 1 electron from the 4s, then from the 3d remove 2, that's going to give us the 3. So we are going to have 3d 3. This is simply what you get, because we always consider 4s to be disrupted first as compared to your 3d. So if there's any disturbance that you want to create, 4s has to be affected first, because 3d is more respected. So the expected one and the actual one, they are like this. This is what we have. But then this guy here, they had removed 3 electrons. So that's the reason why you are seeing a 4s0 here, because we removed this single electron there. We're left with 2 more to remove. So we remove the 2 from the 5. That's the 3 that you are seeing. So this will be the configuration for the chromium 3+. Yeah, so please don't take this lightly. Always show the difference between the actual and expected. It shows that you understand the levels of energies between the 4s and the 3d. Because technically 4s is bigger than 3d. So we're just saying this is initially, or it was supposed to be after 3d because it's outside. We mentioned to say the number in front tells us the what? The shell, or the amount of energy that we're dealing with. Yeah, so 4 means that we're dealing with the 4th ring. So the third ring must be satisfied first, or a bit happy as compared to the 4th shell. Any questions, guys, here?